Okay, welcome back everybody. And as you've probably seen from the weekly schedule, this microphone is not the best one. I have to reduce a little bit the volume, but you can still hear up here, right? That's good. Okay, so the topic this week has actually been to extend a little bit upon the neural network stuff, where we're going to have the main emphasis and where you actually are writing a code for. And what we are going to do now is to try to end and wrap up this discussion of deep learning methods. And we are going to focus on something which is called recurrent neural networks. And this is also kind of technology which is widely used, and especially in connection with language processing, text analysis, but also in the analysis of time series. And that's something which, from a more kind of natural science point of view, is perhaps a little bit more interesting. But I mean, the kind of applications are really, really many of these methods. So what we have seen till now is a standard feed-forward neural network, which we normally call for an affine. This is based on an affine set of transformations, where you typically have full matrices which are multiplied with either a matrix with the input or the matrix of the weights or vectors. And then, based on that, you could then, with a backpropagation algorithm, you could then find the weights and the parameters of that specific architecture which you've chosen. This is normally something which is very data greedy and CPU intensive, because we do not reduce the dimensionality of the problem. Then, yesterday and last Friday, we went into the topic of convolutional neural networks, which are very specialized methods for image recognition. So if you're going to deal with some kind of image recognition or recognition of patterns, then the CNN would be the kind of favorite method for many of these type of applications. Now, when we now dive into recurrent neural networks, which are actually very data greedy and data intensive, because you can think of this as a set of neural networks which are coupled together, and where the dimensionality reduction itself is normally not done unless at each step you actually plug in a convolutional neural network. So we are going to see how you can actually do these things. And again, we are going to, in a way, just scratch the surface. So I want to give you the kind of overarching ways and the overarching mathematics, but we are not going to have a project where you write a code for a recurrent neural network or a convolutional neural network. If you want to, you can do it, but normally what we recommend is that you use this application programming interface, the API Keras, which interfaces well with TensorFlow. For those of you who plan to take the imaging course in machine learning, IN 5400, then you will normally use PyTorch, which is another programming environment for deep learning. And then you can actually program in more detail the setup of a recurrent neural network and a convolutional neural network. So obviously, by obvious reasons, since this is a kind of more introductory course with an emphasis on the mathematics, there is a limit to how much we can actually go into gritty details. And in our case, Project 2 defines the kind of level of complexity when it comes to your own programming, where we actually write a neural network code, and the backpropagation algorithm kicks in all these kind of methods. So when we're looking at recurrent neural networks, you will also recognize where the backpropagation algorithm comes in. So when you've done it once, it's easy to transfer that one to other types of deep learning methods. Okay, so what we did yesterday was to go through some of the mathematics. So there's a mix of slides and codes which you'll find in the Jupyter notebook, and as well as the handwritten notes. So some of these things are things which I haven't plugged in fully in the lecture notes, as you have seen. And what I normally recommend then is actually, if you want to look at all these nice images put together, there are these lectures from Stanford. And I borrowed heavily from those when it comes to own images. So if we now go down to the topic of neural networks with recurrent neural networks, what I wanted to tease you a little bit with first is a simple example, and then we're going to look a little bit more at the basic setup and how you can eventually, if you wish to, define a recurrent neural network code. So today I'm going to use both the whiteboard. I'm going to run some codes with examples, and we're also going to look a little bit into the nicer figures which I've stolen from these lecture slides here. So there's a simple example here where what I'm doing now is to define a function which is a sine function, as you see here. So that's the function which I want to train to, and t defines a time. And as you can see here, I've defined 1,000 time steps. And what I'm going to define now is that the first 800 time steps are going to define my training data. And then the remaining 200 time steps are data sets which I'm going to use the model on to make a prediction. So I'm going to train the model on this sine function for 800 steps, and then I'm going to make a prediction for steps 801 to 1,000. Does that sound reasonable? So I just keep the first 80% of the data as my training data, and then I want to make a prediction. And to do this, I'm actually going to use recurrent neural networks. So let me show you how you could code this in a very simple way. So the first thing is just a plotting of the data. It's a sine function. I guess that's not very exciting. So what I could do now in the first run is just to take away the noise here. And then I define my train test in terms of these values, as you can see. So the train set is now the first 800 steps, and the test set is now the final set of steps. And then I set up my recurrent neural network. And in this case, I'm going to explain a little bit later what these new units are. So the input shape is actually the one given by the training test. And I use the ReLU function as an activation function in every single unit. So when we now decode this, we're going to look at the way we can read this setup here. And then you can also see that there is I'm adding a dense net. So I'm actually producing a simple recurrent neural network, and then I feed into a dense neural network. And this compiles also finally the mean squared error. That's the kind of how to say the error function which I'm going to gauge my model with. And I use the root mean square propagation as the way to optimize my learning rate. And then I make my training and I make my prediction based on that. And this kind of setup is pretty standard. And then I plot the prediction and the training data. So if we just run this, so these are calculations which normally are going to take a little bit more time. And this is the training data, just a sine function, nothing exciting. And then it's now running through the data. You see the number of parameters which we have for the simple recurrent neural network. We have not that many, some 1,100, so it's not a big system. And then the total number of parameters you can read here. It's running through a given number of epochs. And at the end here, so this takes a little bit more time actually than if I just were to perform a kind of linear regression, which would be actually much faster than what I'm doing here. But this is just to illustrate how you can set it up and how you would run it and what you might expect to get. So you can see now the blue line is actually my, I should have increased this font a little bit here. So you can also see the loss function here. The difference between the training data and the test data is actually pretty good. It's 10 to the minus 4. And this predicts also the mean squared error for the test data. So this is something you can say is pretty good. And if you go now to 0.800, from 0.800 to 1,000, this is just a prediction which I make with my model. And the first 800 points This is basically my training data, and then I use a prediction, the model which I have, on the training data. And then I make a prediction from 800 to 1,000. Obviously, if I were to include some noise here, this wouldn't look so nice. So if we just repeat that, and I guess you're pretty familiar with that now, that as soon as you add some noise to your data, then things normally worsen quite a lot. So if I were to do this and just rerun now, you will then see the data looks like this, and then your predictions are not going to be as nice as they were in the previous case when you had no noise. But this is basically expected. I mean, I guess what you're going to see here now is not something you would not have expected. So if you look at the loss function which you get, or the cost function, it has a pretty large value. In the previous cases was 10 to the minus 5, 10 to the minus 4, and now we have something like 0.4 something. And if you look at the plot at the end, so it takes some time actually, and it should be done now because it should have only 100 iterations, 100 epochs. You can then see the final result here. I should plot this, I should avoid this kind of windows being shown here. But you can see, suddenly me not being able to touch my touchpad properly, but you can see the results here. So the red one is my prediction, and the prediction is now not as good as it was in the previous case. But clearly here you could make a more complicated architecture, but that can easily lead to overfitting at the end. So when you have noise, I mean, the quality of the results may be so and so. But you saw that when we had the no noise case, this was actually something which gave a very, very nice prediction of the results from 800 to the 1,000 step. So this is a typical example on how you could use a recurrent neural network. So let's now try to demystify what this is about, okay? And let me now switch back to the lecture notes, to the whiteboard. So let's stop this one. So till now we have been doing fully connected neural networks, or we have reduced the dimensionalities. And what we're going to look at now is the mathematics of a recurrent neural network and how we can set it up. So let's just write this here, recurrent NN neural network. And what we're going to do first is actually to look at a simple example, which I'm going to use to give you a kind of feeling of what a recurrent neural network, the way we can interpret it. So as an example here, we're going to consider a well-known differential equation. So we have an ordinary differential equation, which now could be interpreted as just a variant of Newton's law. So where you have the acceleration first, you have some velocity dependent term, dx dt, and then you have some position here, which depends on time, and then you may have some external force which you're adding here, which depends on time. So this is probably an equation which many of you have seen before. It doesn't need to be a rephrasing of Newton's equation. It could be something which represents something else. But now you can think of velocities and positions, which is a pretty, a pretty simple system here, where you can think of an object which is moving with a given acceleration, velocity, and under the influence of some kind of external force. The way you would solve this is obviously to discretize, and you would start with some initial conditions. So you initialize your system, and this is what we do when we set up a neural network anyway. So we have some initial conditions, which would be some x0, which could be x at the time t0, and then you would have the velocity 0. So this is a known quantity at the velocity at t0. So we need these initial conditions to start the solver. Now, the way you would start the solver is to implement something like Euler's method, right? So the simplest way we can look at these equations is by Euler's method. And in that case, we would have a discretized value for the x's and the velocities as well. So that's going to be given by an x of I plus a delta t. And then we have the derivative of the position, which is actually the velocity. So this will be v of I, because we know that the v is actually dx dt. And the only thing we've done now is actually to implement an algorithm, which is called Euler's feed-forward algorithm. And that gives us a way by which we can integrate up the positions. So these are coupled differential equations, which means that we have a similar differential equation for the velocity. And you know that the velocity would then be written something like this, dv dt. And I divide by the mass. So I have this term here, just shift to the other side, times m, and then I have the velocity minus 1 divided by m times x, plus this applied external force divided by m. And I'm just skipping the time dependence here. So this is something which we could rewrite as an f tilde, where this f tilde is defined by this quantity here, f divided by the mass, minus a parameter alpha times the velocity, where alpha is given by this ratio, and then I have a parameter delta, where delta is given by this quantity multiplied with x. So that's the derivative for the velocity, and that means that I can set up a scheme for the velocity as well, where I would have a v of I plus 1, which is equal to delta t times this f of I tilde minus alpha v of I minus delta x of I plus a v of I here. Now, this is something which I could now rewrite in terms of a function. So let's just call this a function f. And this function here depends on the previous value, v of I. It depends on this f of I. And then it depends on x of I. So you could just sandwich these different quantities into just one generic function. And then you know that when you have the specific values, you simply know that, okay, this is going to depend on this v of I. You will have a v of I here, a v of I here, you have your x of I here, and you have your f of I here. Okay? Nothing special here. Now, the reason why I'm doing this is that I'm going to rewrite this in terms of a diagram. And the way you could think of this now is the following way. If we now just specialize at v, so let's look at v only. And the way you can think of this now is that you start with an initial value, v0, and that feeds into this function f of 1, and it gives us also an output. So we could now say that this feeds out a value. So I'm just going to write it like this, v of 1. So that's the next value. And then it receives as an input this f of I, and this is f of 1 and x1. That is the input to this specific function. Now, it gives, you could now think of the following setting, that you actually are making a measurement of the velocity at every time step. So you're feeding in a force, you're feeding in a position, you know these parameters, and then at every time step, you measure the velocity. So the type of measurement you're making, I mean, we're not going to specify that, but just imagine that you actually, this is your output at a given time step. Now, in our specific case, this now is also given in, this V1 feeds also into F2 at the next time step. And at the next time step, we also apply a force. We have a given position, and we measure velocity. Now, this continues now all the way to the final time step, which will be some f of tau. That's the final time step where we made these measurements. And we have a force f of tau, we have a position x of tau, and this produces a velocity v of tau, and it also outputs the final velocity. So this will be the final velocity of the system here. So what you could think of now is that there's some kind of external probe which acts on your system. You know the value of this force, you know the position, and you measure the velocity. And this is a typical example of a time series of measurements over given times. And what you could think of now is that these functions f's are now going to be replaced by the architecture of a neural network. So in our specific case, what we have is an explicit function which we know how to handle. So instead of, and as we've seen with neural networks and convolution neural networks, the function which we're looking at can be replaced by the architecture of a network. And this is what we're going to look at now, how we can actually translate this simpler example in terms of a neural network model, where we now have measurements at every time step. So what you could think of now is that what you're doing is that your network produces an output at every single time step here. So you produce an output, so this is V1. So we could put a tilde on top of V1 and say that this is what the model produces. So we can get a little bit more sophisticated and change what you see here into the following. Because if you go back to what we have here, this F, this is a model. We have implemented Euler's method, which is nothing but a way to solve a differential equation, and it will not necessarily give us the exact velocity. So the way you can think of this now, in terms of the neural network way of thinking, is that we can modify this image a little bit. So I'm going to put a V0 here. So this is the initial condition. That feeds into some F1. This produces an output, V1, and then this output is now going into a cost function. And I call this C1, and that receives, so I'm going to change this V to a V tilde, because this is what our model produces. And then I have a measurement, a real measurement. And this real measurement is the one I want to compare my model with. And my model receives an input here. So this is my F1, X1. And then we just feed in this new velocity, V1. That's fed into this F2. And then we have an F2 here, an uppercase F2, X2. It produces an output, V2 tilde. And that is fed in to the cost function again. So often this could be just a mean squared error, for instance, just to give an example, like the one we saw here. So just think of this in terms of the sine function which we have. And then we have a V2, a real measurement. And this continues all the way till the final time step, where we have a final measurement. And then we have an F of tau, X of tau. This produces an output, V of tau tilde. It feeds into a cost function, C tau. And then we have a final velocity we want to compare with. This is our final measurement. And we can actually put it like this here. But that is just the final value, and that's compared with the final measurement we have. Then what you could think of now is that you could have all these cost functions for the separate time steps, which feed into the total cost function. And that's the quantity you want to optimize. So if you look at all these cost functions, we could actually call them loss functions, because I like more to use the loss function as the individual contribution and the cost function as the sum of the individual contributions. So then you would have a total cost function, which is the sum of all these small loss functions, and that's the quantity you want to optimize at the very end. So this actually, this kind of simple example is the one which lays the foundation for a recurrent neural network. So let's try to look a little bit more in depth into how you could set up a recurrent neural network. So what we have now is this layer with a cost function. We have a model, which is the F1, and this is something we are going to replace with hidden layers and different types of hidden layers and how they are connected. This is something which will define the architecture of a recurrent neural network. So let's take a closer look at that and look at specific ways of doing that. So in general now, what we could think of, instead of having this velocity, v of I plus 1, we could replace that one with an output which we call s of I plus 1. And that this s of I is something which now depends on a specific function, h, and I'm going to use h because this is going to represent hidden layers in my neural network. So I want to generalize the case which we had, and what we have now is something which may depend on the previous value. It can depend on some input, and then we are going to have the parameters theta. So theta are going to be the biases and the weights of a neural network. And we would typically write this as an h of I here. If we look at the overarching structure, we could now think of this S0 here, which now feeds into a chain of these S's. So we have an S of I minus 1, which receives an input, X of I minus 1, and this feeds into an S of I, and then we have an X of I here. This feeds into a new S of I plus 1, and we have an X of I plus 1. And this goes all the way to the final result, which I denote with just this box here. So this S is now given by a function, and we could now think of this function in the following way. So we have this H0, which now feeds into some H1. So this is our hidden layer, and this receives an input X1, and this produces an output Y1 tilde. And this Y1 tilde is now going into some cost function, which I call for C1, and that has a value Y1 here, where we compare the Y1 tilde with. And this proceeds to an H2, and we have an X2 in here, that produces a Y2 tilde, and that is fed into a new cost function, C2, and that receives the output, Y2, which we want to compare Y tilde with, and this just continues all the way till the final layer, which I just wrote right with a circle and some slashes inside. And this is something which you normally would see written as a box like this. There is an R and N, and then we have an X which is fed in here. We have a Y which is fed out. This is the Y tilde, and then this has this kind of loop here, which is meant to indicate all the different hidden states here. So these are different hidden states. So what we're going to do now is actually to look at one of the types of architectures which is pretty common. So let's look at that one. So what we have then is now the following. So let's break this down. So we have some input here, and we initialize our system. I just write it like this. And then there's a set of weights here, and this set of weights are propagated into a hidden layer at time t1. Then you feed in some external value, t minus 1. This could be like we had for this differential equation, a type of external force which is applied to the system. So we know exactly the value of this. Then here, what we need then is a set of weights again. So we need from the input at a given time step, a set of weights, and that's represented by this matrix U. The previous hidden layer connects with the next one with a set of weights W. Now again, this hidden layer here produces an output, and we indicate that with a matrix V that contains the weights which connect the hidden layer and the output. So we produce now in here, we produce a Y tilde of T minus 1. And then I need to squeeze in a little bit here. So this one is now fed into the cost function, C of T minus 1. And that receives an input of Y of T minus 1. So that is a measurement which we have made at the time step T minus 1. So the cost function is obviously something we have to define. In that simple case which I showed you, the cost function was just a mean squared error. And that was computed at every individual time step. And then you can compute the total cost function, which is the sum of all the individual time steps. Then the next step is then to propagate again to the next hidden layer, and we will have a new set of weights. And we have a new input, xt of u, and we have a new output here. So we have a yt. So what you see here is actually the same thing as your standard neural network. So the way you could think of it at every single time step, you could think of you setting up a standard neural network where you're training the parameters of a normal neural network. The only difference is that they are connected with a previous hidden layer at a previous time step. And then it links with the next time step. In some type of models, people often run with the same weights for all the layers, but you could also think of training the weights for every given time step. Now, what you see here, this h of t minus 1, h of t, it doesn't need to be a standard neural network, a feed-forward neural network. It could actually be a CNN. So when people do image recognition at different time steps, this is something which you could actually replace that with. So you're not limited. So this ht minus 1 does not need to be a standard feed-forward neural network. And it doesn't need to be a shallow network. So the more complicated you make it, the more training time you need, obviously. So if we now proceed like this, so I'm just trying to squeeze this in here. I have a cost function again, a C of t, and that receives the output, which we have as a measurement. And this just continues all the way to the final layer. And I just make this, I denote that one with this blob here. So that's an example of what we might call a standard recursive neural network. And what we need to do then is actually to train these different parameters. So the parameters which we need then is actually to set up some z of t. So we need to define that one. And that's going to have a bias. We are going to have a weight, a w, which then links with the previous hidden layer, t minus 1. And then we have a matrix U, which links with the input at x of t. So this is the x of t at the time step t. Then what we do next is that we produce an output, h of t, which now is given by some activation function. So this could be an activation function of the type of a ReLU type. It could be a tanh, it could be a sigmoid function, or whatever we are dealing with. And this takes as input this z of t. The next thing which we need then is to set up the y of t. So y tilde of t is now given by some function, g, let's call it just for that. This is another activation function. And that's going to have this h of t multiplied with this weight matrix V plus a C here, which is the bias. So if you look back at the image which we had, you see now that we have the input to HT here. That has a weight multiplied with the output from the previous layer. And then we have the input coming in here, and that's given by this weight matrix U multiplied with X. And then when we are setting up the output to Y, then we have a new function which modulates the final output, and that's given by the output from the hidden layers multiplied with a matrix V plus a bias C. And that bias is just a set of vectors. So G could be a function like the softmax if we're dealing with a classification problem. It could be just the output if we are dealing with a standard regression problem, just the values which are produced. And then these are fed into the cost function, and then the cost function is computed using the output values you want to compare with. And that would be one training step, and then you move to the next time step, and so on till you have reached the final value. So the final cost function takes now as input. So if you look at that one, so the cost function at each time step is now given by this function C of t. And that function C of t takes in x of t. It contains this h of t, contains y tilde of t, and then it contains y of t here. And then this is one of the quantities which we want to minimize. Now, one of the drawbacks here is actually that you have to compute the gradients of this loss function with respect to the parameters. That's something which becomes very expensive from a computational point of view. And you need a forward pass from the initial starting value, so from the left to the right, and that's going to be followed by a back propagation step. So what you're going to do then, when you're training your network, is that you will typically start at the initial time, 0, and then you propagate this through the network, and you compute the loss function at every time step because you have a specific output. So the whole system is set up so that you have, at every single time step, you have an input and you have an output. And these are the data which you feed into the network. And the input is obviously fixed, and the output is also fixed. And then the output from the model is the one you're comparing with in the loss function. And then you calculate the derivatives, and then you move forward. So you propagate all this information forward. And this model is actually called back propagation through time. And in this specific case, we have a full memory between the different hidden layers. So if you look at this system here, the hidden layer, which you see here, is fully connected with the previous hidden layers. So it has a memory of what was going on in the previous stage, and this is just propagated throughout. So what you would see here when you're setting up the algorithm, this is something which is now called a BPTT, and that is back propagation through time. And it means that the network then, as I said, it's going to be pretty heavy to train. And in order to set up everything here, you need to calculate all these different matrices. You could actually keep the weights the same when you move through the network, or you could actually allow it to train different weights for every given time step. Now, there's one way by which you could now reduce this complexity, because this becomes time expensive. And you saw that simple case which I run with a very shallow network. It took actually quite some time to fit a sine function. If I were to do linear regression and just set up the training data, I would actually solve that problem in just a few milliseconds. So clearly, running that case with a recurrent neural network is something which is very time consuming. Yeah?
What about the weights after a sequence of time steps?
So this is also something which is done. So you can actually calculate the weights at different, so people actually do that. So you want to update the weights before a given number of time steps. So we are coming back after the next lecture, different ways by which you can reduce the computational complexity. There is also a problem with this type of calculations because you are propagating forward and backward these different weights, and they can explode in dimensionalities because you're just multiplying them all the time. If you look at the sequence here, what you end up with is a series of matrix multiplications again and again and again and again. And that can lead to exploding gradients. And what is common to do then is actually, one, to calculate the gradients only in certain instances and update them. So you actually have several nodes which share the same weights, or that you actually do a chopping of the gradients. If they become too large, you put them back to a given predetermined value in order to avoid exploding gradients. Yeah?
Yes, particular situations where either one of the schemes are more applicable?
I think this is something you would have to look at from case to case, and you cannot tell a priori whether that will be the case or not. But it's pretty common. I mean, some of these solvers, they actually have default values. And I think one of the default values is actually you use the same weights all the time. But this, if you write your own code, you can actually play around a little bit with the data like that. Okay, so let's look at the way by which we can reduce the complexity. So let's take a look at the reduction of computational complexity. And one of the standard models which is also used is actually to not link the different hidden layers with each other. So you're just taking the output from the previous layer and you feed that one into the next hidden layer. So that means that the network is going to look something like this. So you would have some kind of initial value of y here, and I'm going to put this parenthesis here just to indicate that this is my initial value. And that feeds in to the, after some time, so you can think of this circle with the dotted lines is meant as an intermediate, it contains all the intermediate steps till we reach a time step, h of t, now t minus 1. Now this receives an input of x of t minus 1, and then we have the weights which connect the input to the hidden layer. This produces an output, and this is linked with a matrix V here, and this produces an output which we call y t minus 1 tilde. This feeds in to the cost function c of t minus 1, and that receives an input y of t minus 1. This now is fed into the next hidden layer, and then we have the weights. So this should actually, this looks like a W, but it's actually a U. So, and then I have a W here, which now feeds into the next hidden layer, h of t. This receives an input x of t here, and I have a U here, and this produces an output y tilde of t, and this is fed into the cost function c of t, and that receives an input y of t to which we compare the results. And this proceeds again to the next hidden layer of h of t minus 1, and this just continues all the way here. I'm just putting up arrows like this. Now, if you look at these different types of networks, what happens now is that this new system is actually in a way almost independent of the previous one. So the only thing it receives is an output from the previous layer or the previous time step. Now, if you look at this model which you have up here, if we now compare it, and if you're familiar a little bit with parallelization, This model which you have there is extremely sequential, which means that it's almost impossible to parallelize and subdivide in given tasks. So you actually have to run sequentially through the whole network. And that becomes, it's time consuming, and it cannot be very much made more efficient when you use parallelization. If you look at the next one, on the other hand, this is a network which actually tends to train not as well as the previous one, but it can be easily parallelized, which means that you can actually rerun this many, many more times. So there's always this kind of trade-off between the accuracy of your calculations, how many calculations you can run, and the number of cycles you're willing to spend and willing to wait before you see the final result. Yeah?
Could it in this case be relevant to have information about not only the previous time step, but the step prior to that?
Yeah, you can do that actually. That's correct. That's correct. That's a good point. Okay, I see I'm running a little bit over time here. So I'm trying just to break down things with a whiteboard. I hope it's not too boring. But this is a kind of structure which we have to deal with when we are setting up a recurrent neural network. And just keep in mind the simple model with the differential equations, because that gives you the kind of one way to visualize what is going on. These kind of networks are very much used also in language processing. And you can actually, and they have been extremely successful in that field. Okay, should we take a small break? Is that okay with everybody? So for those of you online, I'm going to put the recording on pause. So when you now look at the computation, so these two setups, they are two of some of the most common setups for recurrent neural networks. We have many other different ways of doing that, but we're not going to touch upon everything here. I just wanted to mention one technique which is used, which deals with the computation of the gradients, and this is called gradient clipping, because the recurrent neural networks have the problem that you can easily end up with gradients which explode in size. And I just wanted to show you what can happen when you have exploding gradients. So the other thing which I wanted to quickly mention, if you now look at the training which you need to do, we see that now we have the input to the different hidden layers. We have the output from the hidden layers, this y tilde, or at a given time t. We have these different activation functions. So like this y tilde, this function g could be a softmax if you have a classification problem. So what you need then, if you look at the drawing of the network, you need obviously to calculate at every step here, you would need to calculate the gradient of the cost function. That means again that you would need the gradients of the cost function with respect to the weights. So all the weights, you need it with respect to the biases. And you need, so that means that you need to have derivatives with respect to these parameters, with respect to these parameters, and the biases here, and the biases which are included here. So that means that you need at least 6 derivatives here of weights and biases. So that means that the calculations in terms of the backpropagation becomes a little bit more involved, but it doesn't need to be that. Many of these methods, like this simple RNN, which I put up, has normally just one hidden layer. But you can stack them and make them as deep as you want, but that clearly means more CPU expenditure in order to train all the weights and biases. But again, this is something you have to try in order to fit the kind of data you are looking at. And this hidden layer here, or the different layers which you have, which we have set up here, they could equally well be replaced by a CNN, if that is of interest. Or you can stack together CNNs with standard neural networks, depending on the type of problem you're dealing with. Now, the cases which I showed you are pretty simple ones. I mean, reproducing a sine function, and I've been using it mainly also for extrapolation based on a certain training set. And I will show you an example of a typical extrapolation problem later. Okay, so one of the problems we face when we are dealing with these kind of recurrent networks is actually the problem of growing gradients. So the typical problem, let's just write it here, problem with CNN or with RNNs are often due to exploding gradients. And there's a simple way to understand that. So let's now take a look at the output which we have, and let's just simplify the way we set up the output. So suppose now that we feed in to this layer, this hidden layer, we now feed in a weight matrix multiplied with the output from the previous time step. So this is one of the typical matrices which we have to compute. We have to compute that matrix multiplied with the output from the previous layer, and that gives us the input to the next layer like we discussed here. So we would have a input which comes from the previous layer. This is weighted by this weight, and then it produces the input to this specific layer. So in principle, this is just given by a matrix times a vector, or matrix times a matrix. Now, what we are going to do now is that this operation here is actually repeated many times. So this operation gets repeated a given number of times, is repeated for this quantity h of t. This is repeated t times. Because what we have done now, if we assume that the weights are the same from the beginning, so then we would have an h of t, which is now given by w to the power of t multiplied with h0. So the first initialized parameters, or the hidden layers, are then multiplied again and again with this weight matrix. So you can, as we discussed before the break, you can have networks which are trained with the same weights, or networks which are trained at given time intervals. Let's now assume that we use the same weight matrix again and again and again, because that allows us to extract some simple mathematics here. Now, what you could do next, this is actually an example of the power method. So you could now think of, if you now look at the eigenvectors of this matrix W, so this matrix, you can find a orthogonal matrix which diagonalizes this matrix, S of t, and the eigenvectors would then be, so this matrix S times S of t is given by ST of S, and that's an orthogonal matrix. And we can perform a transformation of the matrix till we have the eigenvalues of that matrix. That's a standard way by which we find the eigenvalues of a given matrix. So what we could do now is that these eigenvalues, so this matrix D is now given by the eigenvalues, lambda 0, up to some lambda of the dimensionality of the matrix. And then the rest of the matrix elements are 0, obviously. And let's assume that it has eigenvalues lambda I. So it has eigenvalues. So this matrix lambda, eigenvalues of W are lambda I. And what we could assume now is that we could define these initial parameters, H0, as a linear expansion of the eigenvectors of the matrix W. It has the eigenvalues and it has eigenvectors, which we just label with a Wi here. So what we could do now, since this matrix has a set of orthogonal, we assume that these are orthogonal eigenvectors, we could now assume that we can expand this H0, the initial values, in terms of these eigenvectors multiplied with a coefficient. This is a standard technique. So we have a basis, and we use that basis to expand in terms of and define a new quantity H0. So let's just make that as an assumption, okay? So this is a way to initialize your system. Now, if you now look at this, if you now apply this matrix W on H0. So this should be H1. That is nothing but the sum of I and alpha I, lambda I times Wi, right? Because what I have is that W multiplied with Wi is given by lambda I multiplied with Wi. Okay? Does that sound okay? So when we repeat this t times, what happens then? T times. Then we have W to the power of t multiplied with H0. That is going to be equal to this sum again of alpha times lambda I to the power of t times the eigenvectors of the matrix W. And now we have made the assumption that the weights are the same all the time. We make also an assumption that these eigenvectors are ordered as an ascending series, no, descending, sorry. Lambda 2, and then up to some lambda d here. Then, what we see now is that when t is large, the value which is going to dominate is actually the first one. Then what we could say then is that this h of t is going to be proportional to this lambda 0 to the power of t times the eigenvector omega w0 multiplied with alpha 0. So what happens then is that you see now that at the beginning, if this eigenvector is large, then clearly you will get a very large value for the action of the matrix W on these different hidden layers. So if lambda 0 is larger or equal than 1, we may get contributions that explode to h of t, which become very large. And that can give rise to what we normally call exploding gradients. So, and that can give rise to exploding gradients. And that's an unwanted feature in the training here. And that's where the technique of gradient clipping typically comes in. And the way gradient clipping functions is that if the gradient exceeds a certain value, you just set it back to a previous value, a small value. So if this happens, it's pretty common to actually reduce the size of the gradient in the next steps, time steps. And that leads to the technique of gradient clipping. So let me just mention that quickly. To avoid this, it is common let me just correct that one. To use what's called gradient clipping. And that means that if you compute the gradient, so suppose you have a gradient g, so we have computed that one, and then you would typically have a statement that if you compute the norm 2 of the gradient, and if this is larger than a certain value, then what you would do then is actually to compute the gradient by setting it back to a certain value where you divide by the norm of the gradient, norm 2, and where epsilon is a small parameter, and then end if. So this epsilon is a parameter you would choose, a small parameter, and then you would typically set the gradient back to a smaller value, and then you would continue to iterate. So this is actually a problem with these type of networks because what you're doing then is you're multiplying again and again with this weight matrix from hidden layer to hidden layer. But this is a technique which is also used in other connections. You have exploding gradients in a standard neural network as well, because you can actually get an activation function which produces a large output, and that can again give rise to a large gradient. And in that connection also, you would typically then clip the gradient. That's a pretty standard technique. We have no guarantee from the very beginning whether the gradient will actually explode or not. So the training of the recursive neural network is normally done using this backpropagation through time and the standard gradient descent algorithms which you have met before us. And to calculate the gradients, you need to keep the internal RNN values in memory. So that's another thing which is important. So this is also a standard RNN is a memory intensive procedure. So that's why many people tend to avoid the back propagation through time and just replace that one with the method where you don't connect all the given hidden layers at the given times. Okay, so one of the things I also wanted to say a little bit about before we conclude this is actually to show you some examples on how you can use these recurrent neural networks. So I've mainly been working on topics like extrapolation and solutions of differential equations. And here there's an extrapolation example. And in this specific case, there is a data set which I have. This is my training data set. And this is a data set which goes in steps of 2. So it goes from the value x2 to 42 in steps of 2. It's actually the calculation of quantum mechanical energies. And the calculation with the 42 here is a calculation with 42 particles. And in that case, I've calculated the energy, and the last points here are very expensive computationally. So then you're asking yourself whether you could use this kind of recurrent neural networks to actually train and then make a prediction for those data points you would like to avoid to calculate. So a typical example here, we are formatting the data. So for typical standard machine learning algorithm, the training data has a form of x and y. So machine learning algorithm learns to associate a y value with a given x value. And this is useful when the test data has x values within the same range as the training data. For this application, however, the x values of the data are outside of the x values of the training data, and then the traditional method of training a machine learning algorithm does not work as well. And for this reason, the recurrent neural network is trained on a sequence of y values of the form y1, y2, which then predicts y3, and then you take y2, y3, and predict y4, and so on. So this is just in terms of pairs. So that the network is concerned with learning the pattern of the y data and not the relation between x and the y data. This is another way by which you could make an extrapolation. Now, the previous case which you saw was actually a calculation of a sine function, which we then used as a training data, and then we use that to make the prediction for the last 200 time steps. So in this particular case, there is a reshuffling of the data. Maybe I shouldn't say too much of this, but the typical hidden layers, the way you would set it up is something like this. So you have in and out neurons, just one. So the input and outputs are just one in this case. I define 200 hidden neurons. And then the simple RNN here has 200 hidden neurons. It has it gets now the input here, and then I can create my dense layer of neurons. And then I have my model inputs. I compile the loss function, which I want to be a mean squared error. And then I have my optimizer, which in this case is an Adam. So this is actually the model which I am using here, the recurrent neural network here, which I'm using then to train this specific data set. And then I can train new points with a trained recurrent neural network, like it's done here. And then I can make my predictions, calculate the mean squared errors, etc., etc. And let me just show you some typical results which you could get. I should actually have, I thought I had run? No, I actually have to rerun it here. So let me just rerun these calculations. So in this case, I have something like, with a simple RNN with 200 nodes, I end up with something like 40,000 parameters. And the calculation is I have 150 epochs, which I'm running when I run the stochastic gradient descent with Adam as an optimizer. And this particular case is actually not that slow. And the data set, I don't have so much data. I had only something like 20, 30 data points. And my prediction here, so this region is where I produce this pair of data, and this contains a prediction for number of particles and for the energy. So up to 42, where I have the final point, I use the red region here to train my model, and the rest here, so the green line is the predicted one, and the blue one is actually the true results. So training my model with these data sets here gives me actually a pretty good prediction. So that's one way to use recurrent neural networks. Now, one thing I'd like to invite you to do is actually take a look at those slides from Stanford, because they contain a lot of examples on language processing, which is something which I'm not too familiar with. So if you're interested in that topic, please take a look at that. In the slides here, you will also find some additional ways of running recurrent neural networks. We have not put that much emphasis on recurrent neural networks in this course. But if you wish to use that for the final project, I mean, I invite you to just take a look at the slides here and different applications. But normally what we have ended up doing is more to look at data like images. So that means convolutional neural networks and also standard neural network training models. As I mentioned, this course IN 5400, which has changed to IN 5410, which I didn't know about. That covers these methods in much more detail. So instead of opening up a fully new topic here, I actually thought of ending the deep learning discussions with this set of lectures. So we have gone through the way you construct a neural network. We have looked at the backpropagation algorithm and how that links with the automatic differentiation and how you can actually train a network. In setting up the neural network, one of the things you're actually doing is also to implement a gradient optimizer, which is a very important part, as you see. Now, all these elements with you training via the backpropagation algorithm is something which enters a CNN as well, as we discussed yesterday. So if you look at the convolutional stage, in the filtering stage, you do actually have series of parameters which are training. And then you have layers where you have no training parameters. When you look at the recurrent neural networks, this is actually the backpropagation through time. So the training of weights and biases is as before. So you need to calculate derivatives of the different functions. But we are not going to develop projects where you set up a recurrent neural network by yourself. So if you wish to use these techniques, if you have problems related to that, then I would normally recommend to use, let's say, an API like Keras. And this is roughly what would be the kind of limits or the boundaries for this course. So I hope you can forgive me if I don't go into more details. That has also to do with the fact that there is a credit overlap with other courses. And this is also a 10 credit course, by the way. So there's a limit to how much we can put into it. Okay, so I don't want to begin with a new topic in the last 15 minutes, which I think is a bad practice. So if you're okay with it, we could just stop here today. So if you feel a little bit bad about that, we can just stay and hang on. Anyway, feel free to ask questions after we're done now. But this concludes my discussion of deep learning methods. And then next week, we are going to start with decision trees and random forests and other topics. And there's only 4 weeks left. Okay, guys, enjoy your weekend. happy weekend. Thanks for coming. Thanks.